Well, it's about time. Yes, about time is the title of this discussion. In fact, the title of a series of discussions on time. We're going to talk about all aspects of time. And time is a very, very interesting topic and a fascinating topic. I'm Nick. My nickname is Nick of Time. At least it is when we're talking about the physics of time. I'm a member, director, officer of the CNPS. The CNPS is a worldwide organization of science professors, very heavy on physics professors, PhDs, and independent researchers. Let me talk a little bit more about the CNPS, and my first quote-unquote slide is going to be my t-shirt. Yes, we're going to have a little bit of fun here, hopefully. Critical thinking is the main reason for being of the CNPS. Well, what are some of the characteristics of critical thinking? Well, we're open to challenging accepted dogma, the currently accepted theory, and looking seriously at alternative views, alternative theories. We won't dismiss them out of hand. And of course, for currently accepted theory, we're not going to assume it's incorrect, but we will take a look at the logic, analyze it, and if new data comes up that casts aspersions on the theory, then we're going to take that new data seriously and see where it leads. We're going to do independent thinking, independent research. And we're not going to be awed by hero worship. We're not going to, just because someone has lots of credentials, even if they've won the Nobel Prize, we're not going to just assume that whatever they say is true. We're going to look at what they say and analyze what they say. And also, we're not going to be just go along with group think. If all of our colleagues have a particular view just to fit in, we're not going to necessarily agree with that view. Same with professors. We're not going to go along just because their professor says something. One other item on the chart, we're saying we're going to have physical models. One of the problems we see in modern physics is there are equations, and then people start just doing mathematical manipulations of those equations without being constrained by having a coherent physical theory. And you can go off on these wild tangents of mathematical fantasy and go further and further afield. I know there were a series of papers on what happens at the event horizon of a black hole. Well, I mean, that's pure theory. There's no empirical data, no experimentation about that. That would just, you start with some equations and you just keep on going, and there really aren't any constraints, and sooner or later you're going to end up in trouble. So this first talk is just to give you an overview and preview of what's going to come, to make sure that there's a good fit between your interests and what we're going to be talking about. If you just saw the title About Time and thought, oh, this must be about the theme of time in English literature, well, you're in the wrong place. In general, we're going to discuss time from a physics point of view, not a philosophical point of view. Philosophical point of view tends to be, just too metaphysical, too vague. We want to be really concrete and talk about the physics point of view. Now, if someone were to ask you, what is time? Your first thought would probably be, oh, what a simple question. It's intuitively obvious what time is. After all, we all live in time. We all experience the passage of time for our entire life, and we have a very good intuitive feel for what time is. However, when philosophers or physicists tried to give a formal, rigorous definition of time, they just seemed to go around in circles defining time in terms of time. For instance, if you were talking about time and you wanted to use the year as an example and explain time that way, and then someone asks you, well, what is a year? You'd have to say, well, a year is the time it takes for the Earth to go around the Sun in one orbit, and there you've, again, explaining time in terms of time. So it's not an easy topic. Also, we're going to talk conceptually about time and about the logic of time. There will be few, if any, equations, but the fact that we're talking about it conceptually doesn't mean that we're just going to stay at a high-level discussion. We're going to get down into the details where we're going to confine ourselves to talking about concepts and logic. And we will talk about the details, and we will try to treat this fairly rigorously. Next topic will be examining the problems of modern physics' view of time, and specifically special relativity's problems with time. That's what we'll start out with. We'll look at a particular interpretation of special relativity's time dilation. That interpretation says that time dilation causes or describes actual physical clock slowing. However, that interpretation leads to a paradox. It was initially called the clock paradox, and then later the name was changed to the twin paradox. We'll get into that in detail in our next discussion, so I won't get into it too much right now. But let me just say that physics professors might say, oh, there really is no paradox, and besides, special relativity has been proven by the experimental data to 9 decimal places, and all serious physicists know that special relativity is correct, and that special relativity is one of the building blocks of all of modern physics. Well, the first two items are not correct. The last item, the fact that special relativity is one of the foundation building blocks of modern physics, just makes it all the more interesting that it's flawed, because that means that the foundation for all of modern physics is built on a flaw, and that just leads to a leaning tower edifice. So that makes it all the more interesting and exciting. In history, there have, right from the very beginning, 1905, when Einstein wrote his first paper laying out the logic for special relativity, there has been a great deal of criticism of special relativity. And even in the later decades, some of the best known names and most prestigious physicists have had problems with special relativity, and particularly with its time dilation. For this discussion, when I talk about time dilation, I'm going to just talk about special relativity's time dilation, not general relativity. So when I use time dilation, it means special relativity's time dilation. For example, Herbert Dingle, who was very well respected proponent of special relativity in his era, head of physics department in an English university, well-regarded university, author of textbooks, proponent of special relativity, until he came across this so-called twin paradox, and that led him to say, well, time dilation is wrong, and maybe all of special relativity is wrong. He was then called a quack, and his reputation was ruined. But when the other physicists like E.G. Kullweg said, well, all his opponents agreed that Dingle was wrong, but they couldn't agree on why he was wrong. In addition, Chang, then of Harvard, wrote an in-depth paper about the twin paradox debate and concluded that Dingle's opponents didn't address the questions that he raised at all. And we'll find that Dingle was correct. So we'll do an in-depth review of the logic of both sides of the twin paradox debate, and you can decide for yourself what the answer is, where you stand. But this will be not only a fascinating discussion of time and time dilation and special relativity, but it'll be a great exercise in critical thinking. We're going to put up two opposing views, and it'll be up to you to decide which set of logic arguments carries the day. Next, we'll review the empirical data from on atomic clock rates as a function of velocity. And I contend that that data will agree with our assessment of the twin paradox. We'll also look at other interpretations that relativists have of the time dilation, such as there is no physical clock slowing, it's just observed clock slowing. But this is a contradictory, mutually exclusive interpretation. So if the physics community accepts multiple contradictory interpretations of this construct, you have to wonder if something isn't wrong. There has to be something wrong. And we'll talk about the pros and cons of other interpretations of the time dilation equation. And it'll turn out that all of them have flaws. They have to have flaws. In addition to time dilation, we'll look at special relativity's construct of relative simultaneity. And we'll discuss how that removes the essence of time from special relativity's space-time model. Specifically, with relative simultaneity, you get rid of the construct of past, present, and future, which most of us would consider as kind of an essential property of time. So we're going to look at how we can put that essence of time back into physics models. Next, we'll talk about the history of special relativity development, and we'll use that as background to come up with a superior alternative to special relativity, at least in the area of time, how time is treated. We won't go into the whole breadth of special relativity. We won't talk about electromagnetism, etc. And next, we'll look at the global positioning system, GPS, used worldwide, ubiquitous, a high precision system that's used by millions of people. If the system wasn't working, people would be ending up in flakes. And when it was originally developed, special relativity, of course, was the currently accepted theory. And the designer of GPS thought he was developing a GPS on top of special relativity. But then they made a change to GPS, and they thought it was just a change that would make its operation a lot simpler. But they changed from using the special relativity physics model to using the Lorentz relativity physics model. Most of the GPS engineers today, don't happen to have focused on that particular issue, haven't looked at it, haven't studied it in depth, so they still believe that they're using the special relativity physics model. And as it happens, the equations of the two look the same. The physical meaning is completely different, almost diametrically opposed one to the other. Now, GPS is a working model of absolute time as opposed to special relativity's relative time, and a working model of absolute simultaneity as opposed to relative simultaneity. And we'll use that GPS model of absolute time and absolute simultaneity to rebuild how time is treated, and that'll be built on proper time, which is quite different than just the vague concept of time. Proper time is very well defined. It's operationally defined. It makes it especially well suited as a physics construct. And it's absolute and observer independent. So there's little confusion, there's a vagueness, ambiguity to proper time. It's a single meaning, well known. And finally, we'll go on to many other topics such as general relativity and a whole slew of other topics to complete our discussion on general relativity. So, if these are topics that interest you, then join us weekly, and it should be fascinating, and we'll try to make it fun. Thank you.